Hello everybody, my name is Anis Pkakria. I'm a PhD student at Lucie Department of Telecom Bretagne. I'm very sorry for not being able to be with you today. So allow me to present our work proposing an approach to preserve outsourced data confidentiality. I have broken my speech up into 5 parts. I will start by presenting some motivation for this work. In the next section, I'm going to present different intended contributions. In part 3, I'm going to show how we can couple fragmentation and encryption to protect data confidentiality. In the fourth section, I will present a technique for outsourced data querying which preserves data privacy. And finally, I conclude my presentation. Information is probably the most important and valued resource for private and governmental organizations. However, the management of a large amount of information containing sensitive elements is often expensive. Outsourcing data is becoming more and more popular as it offers several advantages. However, gathered information often includes sensitive personally identifiable information which must be protected. Data outsourcing means that this sensitive information will not be under the control of the owners, but under the control of an external service provider. From a financial point of view, data breach continues to be very expensive for companies and organizations. A recent study led by Pennant Institutes shows the growth of data breach cost between 2007 and 2010. Average organizational costs of data breach reached $7 million in 2010. Therefore, the use of techniques which ensure sensitive data confidentiality in case of data breach seems to be very interesting and beneficial for data owners. Clearly, the best solution to protect outsourced database consists of encrypting all data before their outsourcing. Unfortunately, querying data become in this case expensive and can be impossible for several kinds of queries. One promising idea aiming to avoid this problem of effectiveness is founded on the fact that in most relational databases, the association between values of various attributes are most expensive than the values themselves. This promising approach proposed by Sireni et al. In 2007 consists in combining two mechanisms, fragmentation and encryption, in order to protect sensitive information in outsourced databases. Despite that this approach is interesting, it suffers from a major limitation because it's founded on the assumption that the outsourced database is composed of only one relation. Our approach has three main contributions. First of all, the definition of an approach allowing to protect the confidentiality of sensitive information in outsourced multi-relational databases by combining fragmentation and encryption. To meet this goal, we have improved the approach proposed by Sireni et al. Second, the definition of a secure and effective technique for querying data distributed in several service providers. Finally, we improve the security of the querying technique in order to protect data confidentiality under a collaborative cloud storage service provider's model. Now, let us move to the next section in which I will explain the manner of combining fragmentation and encryption to guarantee sensitive data confidentiality. Confidentiality requirements are modeled as a set of confidentiality constraints. Two kinds of constraint has been defined. First, singleton constraint. It's represented as a singleton set. For example, C1 indicates that the values of the attribute A1 are considered as sensitive and must be protected. Second, association constraint. This kind of confidentiality constraint is represented as a subset of attributes. It means that the relationship between attributes of the subset is sensitive and must be protected. In multi-relational database, data owner can require the protection of the association between relations. To meet this requirement, we have defined a third type of constraint called intertable constraint. So, how we will use fragmentation and encryption to satisfy this different kind of confidentiality constraint? Singleton constraint consists of protecting an attribute values. Logically, encryption is the only technique allowing to satisfy this kind of constraint. Association constraint can be resolved by fragmenting involved attributes in a manner that their relationship cannot be reconstructed. In the case of intertable confidentiality constraint, protecting the foreign keys using encryption is the simplest way to secure the relationship between the two tables. However, encrypting only the foreign keys is not enough to keep the relationship between involved tables secure, as service provider may be able to link records of both tables by observing and analyzing user queries. To overcome this problem, involved tables should be split into different fragments, and each of these fragments should be distributed to a different cloud storage provider. So, let's illustrate this through an example. Consider that we have a medical insurance company relational database with two relations, patient and doctor. These two relations are linked through the foreign key IgMed of the table patient, which references the primary key of the table doctor. Assume that we have four confidentiality constraints. C1 is an association constraint defined over attributes, name, and illness. To satisfy this constraint, we will separate these two attributes by storing them in two different fragments. C2 is an intertable constraint defined over tables patient and doctor. To satisfy this constraint, we must firstly encrypt the foreign key, allowing to associate the records of both tables. Secondly, store the table doctor in a fragment which not containing a part of the table patient. Constraints C3 and C4 are singleton constraints. To satisfy them, we will encrypt the values of the involved attributes. However, the use of deterministic encryption will give the same values for attributes CC and NSS in F1 and F2, which allows the reconstruction of sensitive associations. To avoid this problem, we have used a probabilistic encryption. For each record, we generate a random value which will be stored in the attribute salt. After that, for each record, we will calculate the value ANK in which we use the generated random value. Indeed, it's always necessary to allow authorized users to construct sensitive association when querying data. Therefore, for each fragment of a table, we report all original attributes which are not presented in clear in the fragment within the encrypted attribute ANK. So, before discussing techniques for processing query over distributed fragments, let's take a look at the architecture of our proposed approach. It includes three principal entities: a user which attempts to execute query over original database, an entity client, and an entity server composed of various service providers in whom the database fragments are stored. The client entity rewrites user queries by splitting them to create an optimized distributed query execution plan which composed of subqueries and other operations. Furthermore, the query executor executes each of the subqueries over the appropriate fragments and sends back the results to the client. In our approach, we can classify queries into two different types. Queries being able to be executed over only one fragment. Performing this kind of queries is straightforward. So we will focus on queries which require the interrogation of several fragments to be performed. Obviously, for this kind of queries, it's necessary to use join operation in order to combine results returned from different subqueries executions. There exists two different ways to perform this join operations. The first method consists in executing all subqueries in a parallel manner, then join the results in the client party. This method can be in certain cases very expensive in terms of execution time. The second method consists in executing subqueries in a sequential manner, which give the ability to carry out semi-join operation using the results of the previous subqueries. We give an example. Consider that a user wants to retrieve the list of doctors of a patient named Dupont. Since the relationship between the two tables, patient and doctor, is protected, these tables are stored in different fragments. Therefore, the query queue is decomposed into two subqueries SQ1 and SQ2, executed respectively over fragment F1 and F3. With SQ1, the client will retrieve the ID met of the patient named Dupont. We suppose that the server will return phi, which is an encrypted value of ID met attribute. The client decrypts this value and executes SQ2 to retrieve the name of doctor. This method, using sequential execution of subqueries and semi-join operations, seems to preserve the unlinkability between records in different fragments. However, privacy problems comes up when cloud storage provider CSP1 and CSP2 collude to link tuples stored in the two fragments by correlating the history of user queries. To overcome this problem, the client should have the ability to execute semi-join queries and retrieve data from a fragment without that the CSP, which stored the fragment, learning any information about the semi-join conditions values. To meet this requirement, we will use a private information retrieval keyword-based techniques. PAR provides a means to retrieve data from a database without revealing any information about which item is retrieved. Most of proposed PAR approaches suppose that users know the index or the address of the element to be retrieved, which is not the case for SQL queries. Be Sure et al. Proposed a way to access data with PAR using keyword search over several kinds of data structure, in particular B+3. The primary values of B+3 is in storing data for efficient retrieval in a block-oriented storage context. Generally, in normalized multi-relational databases, jointure between tables is carried out on the attributes representing the primary keys or the foreign keys of these tables. Therefore, a PAR server will create a B+3 on each indexed attributes, then the client will use PAR queries to run down the tree and privately retrieve records that match the semi-join condition. So, to conclude my presentation, I would like to say that we have presented a new approach based on fragmentation, encryption, and query privacy techniques, which ensures confidentiality of outsourced multi-relation databases. Future work can improve query optimization and execution techniques to overcome some limitations of our approach, such as nested queries evaluation. It can also include the implementation of our approach. Thank you very much for your attention, and I will be happy to answer your questions.